this video, I'm going to share with you what is average expression in Seurat package. And in fact, it's actually just something that I discovered when I want to do the function, and the outcome is kind of different from the default violin plot. So here's the things. In order to demonstrate it, I try to just use the PBMC data from Sadija Lab, which we can download from their official website here, and I undergo all the standard flow. Okay, so now we have the Seurat data, which is called PBMC. I divided the PBMC data into the cluster based on the resolution 0.5, and we got 9 clusters here. So we can see that for this gene, it's just randomly picking. It's up to 123, and the rest may be just 0. So it's kind of all positive data. I try to plot the violin plot to see whether I got similar things or not. But obviously, in the normal violin plot, we can only get like up to 4 or 6 expression level. The slot is data. So for your information, if let's say you're confused, for the essay part, they always have two slots. For the count slot, it is total raw data, which is the unnormalized data, which is the input from the featured barcode metric. After we run the standard Seurat workflow, we have obtained the so-called data slot, which is the normalized slot. They normalize in a way through the logarithm transform. And so here we use the normalized data. So maybe I try to see whether the average expression y have the 120. Is it because it used the unnormalized data? So this is the count data. So let's see what is the minimum and maximum. The maximum is just 73. So it's not really make sense that the cluster will get like 123, right? So this is why I want to further to discover what actually inside the function of average expression, how they eventually get this kind of the number. We use the function trace. Trace, we able to see what is the code for the function. So here they say this is used something that's called pseudo-bulk expression. Okay, so obviously this is something to do with the pseudo-bulk expression, and that's why I go to this link, which is the place to put all the function and the code here. And let's say we want to find for the pseudo-bulk expression. Okay, so this is the function for the pseudo-bulk expression, and it is like this long. Oh, it's really as a non-programmer like me, it's very complicated and also very long. So anyway, I try to reduce it using the function of pseudo-bulk to see how they actually do internally. So this is how I actually do. The first thing is that they create an object called data, right? So corresponding to all the cell ID, we have the cluster ID. Okay, so next they try to retain those row with at least 0 number, which means that all the cell ID has been assigned with at least 1 cluster ID. Okay, so next we use the library metric to create the sparse model metric. So sparse model metric is kind of like in a way to divide this is the data frame into a metric frame. If let's say the cell ID is within the cluster ID, then it will have a number 1 or just 0. So it's a binary metric file. So it will be something like this. For example, here for the first cell ID, it belongs to the cluster 0. Cluster 0 here is the 1. For the second one, it belongs to cluster ID 3. There is 1 in the cluster ID 3. So it is in a way try to divide them into the so-called sparse metric model. Next thing they want to do is to get the columns, the total of the column. So this is something like this, which means that for the cluster 0, they have 696, which is similar with the information stored in the Seurat object, where they tell us about how many child ID is in each of the cluster. Okay, so this is similar like this. right? So it means that in cluster 8 here, it only have 15 child ID. Okay, so next that I want to do is clean the matrix file just to retain the total of column with more than 0. And I think this is no change with all of them because all of the child ID has been assigned with at least one cluster ID. Okay, so next thing they want to do is like to assign a function. Okay, so this is how where they want to do. For example, I create a simple data frame which is like 1, 2, 3, 4. Okay, so this is the data frame 1, 2, 3, 4. And I get it in a way that 2 column times 2 row. And let's say I do with this function with the stat here is what you want to fit in. I fit in here is in a way that 2 for each of the column. So the function here is divide. So mean whatever here will divided by 2 to get the output here. Okay, so 1 divided by 2 is 0.5 and 4 divided by 2 is actually 2. Okay, so this is how the function works. So come back to here, what they want to do is to fit in the stat here with call sums. For whatever cell here will be divided by the call sum. It's a size factor for them. Okay, so that is how we can get it. So which means that this is originally is 1, then it will divided by the call sum. The call sum which is the 696 to get this. Okay, 1 divided by 696 will get this. And here is similarly for this is the 2 which is 1 divided by 467 to get this. So this is considered correct matrix with the size factor. And next they try to extract another set of data which is from the expression slot. Normalized count data here, and then we have 13,000 of the gene and 2,700 of the cell ID. So this is how it looks like. Very hard to see from here, but anyway we can continue. And this EXPM1 is the way to convert the normalized data back to the exponent value. So and this didn't really change anything for the dimension. And then we can see that these two data used and the category matrix that I have produced just now, they have the similarity which is the 2,700. So this is the cell ID that are similar in these two data sets. And the next thing they want to get back the data is to data use type category matrix. And mathematically, when these two times together, we will remove the cell ID. 2,700 will be removed, and what left is the gene ID and also the category ID. Okay, so let's see how it looks like. The row refer to the gene ID and the column refer to the cluster ID. Okay, so maybe I just try to check that for these two genes that I randomly pick up, it returns something exactly same as the output of the array expression. So this is show how this array expression come out. The main point is instead of just use the normalized data from the Seurat object, they try to undergo one more step, which is to determine the size factor based on the number of the cell ID in each of the cluster. So why they want to do it? What is the benefit to do it? I try to explore what actually means by pseudo box. From what I can understand is you should kind of adopt the approach from this tool, which is called MASCAP, multi-sample, multi-group single-cell RNA-seq analysis tool. So this is the tool in a way trying to reduce the false positive rate in the single-cell RNA sequencing data. It tries to make the distribution of the data set closer to what is in the bulk RNA sequencing, which is like how this is tool or how HR that able to fit the model in that way. Because single-cell RNA, when they do it individually, it can't really fit in the model. So that's why they try to group them based on the similarity of what have been assigned by using 5 cluster function, and then it will be useful when we want to do downstream differential expression analysis using digit 2 or HR model. So this is the main reason that I can see, but I'm not really sure whether it is just stop here or is there anything else that we can explore together. If you have any comment about this issue, please educate me by dropping me the comment or email. So I think that's all for my sharing today. Thanks for watching and I'll see you next time. Bye!